Hello and good morning, and thank you so much for joining me here. It's April 22nd, and I think I've got an exciting idea here about this radio. Yesterday I tried what I imagine is the standard way around the problem I'm facing, which is I have swapped the speaker for this radio with another speaker from another radio, and it doesn't match properly. Specifically, the field coil resistance of this speaker is way high from what this radio is looking for. It's looking for a 600 ohm field coil, and I've stuck in a speaker with a 1700 ohm field coil. That's basically 3 times the resistance the radio is looking for. The result of that appears to be twofold. One is greatly reduced B plus in the radio. Instead of being up around 250, it's down around 150 and lower, much lower in some areas. Oddly enough, the radio does operate even with this problem. Another compounding issue is too much heat being dissipated in the speaker field coil. I did measure it up at 50 degrees C, and it was still on the rise. How high it was going to go, I don't know. Probably not too much higher, 55, 60 maybe. Maybe a little higher under bad circumstances, but seemed to me it would be sensible to try to do something to reduce that. So I installed a bypass resistor here, try to split the current, have part of it go through the speaker field coil and part of it go through the resistor, and the idea is I would half whatever was going through the speaker would be halved in the resistor and the speaker, and voila, B plus up, heat down, everything beautiful. The result of doing that, and I tried 2 different sizes of resistors here, was a near burning out of the resistor here. That to me is unexpected. Now maybe I don't understand something that's always that's just a standard truth here all the time. Maybe I don't understand something. Didn't seem to me to be right. This is a 7-watt resistor, and it was frying up. It must have been dissipating close to 10 watts. The speaker was still operating, so there's some current going through the speaker still, conceivably the same amount of current, since the resistance of this was roughly the same as the resistance of that. This is a 2000 ohm resistor, and that was 1700. In fact, more current should be going through there than through here. So if this thing is dissipating 10 watts, then is that still dissipating 10 watts? And the voltage never came up that high anyway. So the whole thing was the B plus voltage. The whole thing was kind of a flop. So that was yesterday. So today, what I thought of right at the end of the session yesterday was maybe this radio is drawing more current out of its power supply than it should. You would have to think in any dilapidated radio that happens. The power supply, maybe it's supposed to supply, I don't know, 125 milliamps, but instead it's supplying 175 because there's current going places it shouldn't be going because of dilapidation. Well, an example of that was this capacitor burning up over here. Now, there's not a lot of current involved in something like that, so you can't be dumping huge amounts of current off in these components without heating them up. So nothing's heating up. So none of this makes any sense to me at all. I can't fathom how all these puzzle pieces can ever fit together. It's like they've come out of a different puzzle box or something. So my idea is to use an external power supply, that'd be this guy up here, to replace the power supply, the B plus power supply in the radio. In fact, I wouldn't even have the radio turned on at all. Feed power from that power supply into the B plus circuit, examine how much current is flowing in that, and then I can make some deduction about is there a part out here which is sucking back the power, basically. Or I can start doing part replacements and target a few and see if I can find something that cuts the apparent excess current out. Or on the other hand, maybe I'm going to power it up with this supply and find out radio's drawing the right amount of current. And if that's the case, I would just stop and scratch my head and wonder what's going on. Now there is a way out of this. The way out of this is to ignore it. It takes a long time for the speaker to heat up. You could get an hour's operation off this radio before the speaker becomes endangered, I would think. The problem here is leaving this thing running for 3 hours unattended. That would be the real problem. But that's one way out of it. Put a big sign on the radio: do not operate longer than 1 hour. That's called an administrative solution to a safety issue. Administrative solutions are to be avoided at all times. So, and not to be relied on. The sign can fall off the front of the radio. Okay, so I'm going to get ready to do that. That test, I have to study the schematic, understand the B+ circuit, understand where to connect my power supply in, how to prevent the current from kind of going backwards in the power supply and going the wrong way. I think this is all easy stuff, really easy stuff, and we'll see what happens after I stop for some coffee. Okay, quick glance at the power supply here. So the power supply B+ voltage is developed right on this line here. Here's the filter capacitor. This is the one I changed. And this is the only output from the power supply, is this line here. So all I have to do is energize this line. I'm going right through the field. Ooh, you know what? Maybe I don't want to do that. Maybe I want to go on this side of the field coil. Leave the field coil out of the circuit for now. And so I want to feed power in here. So I have to figure out which one of these lines goes here and which one goes there. It's pretty easy. See, there is a jumper from this terminal to this terminal. It's showing this way on the schematic. I can see that jumper, so I can see this. So it's the other. So that's the wire I want. I almost blew that. This is the wire I want. I want that wire. The wire with the bond. Okay. I guess jumper is a better word than bond. Okay, so we're looking down here. Here's the jumper. I want the wire with the jumper. I want to put the positive lead of my power supply onto the wire with the jumper. There we are. And the yellow one just goes to a grounded terminal. I'm just going to put it right on the chassis like that. Now I have a clamp-on ammeter. I have not had a lot of success with this. Clamp-on DC meters, they can be interfered with by the Earth's magnetic field. So we'll zero this. Oops, first DC, I'll zero it. Okay, can you read those numbers? And then I think if I just turn it, they'll show that I don't know what I'm talking about. That's what it'll do. Okay, so I'm going to clamp this on one wire here, like so. So this should give us a more accurate reading, I'm hoping, than the panel meter on the machine itself up here. This panel meter is not very precise, but certainly if things go wild, we'll know right away. The radio itself says it draws 125 milliamps from the power supply. So if everything is absolutely normal, we should read 125 milliamps here. That's really not possible. Yeah, actually, you know what? There's a problem with this test. I'm doing this test with the tubes not heated, so there's no tube current. Now, the bulk of that 125 has got to be tube current. Come to think of it, there shouldn't be much current flow at all doing this test. Okay, don't know what I'm doing, but let's do it anyway. Here we go. So I'm going to just connect up the positive part here. I left that turned up. Shame, 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 shame on you. I don't think my boss saw that I left this control set up. I don't think he saw it, so I think I'm probably okay. We'll find out when my service review gets prepared. So I'm leaving a little bit of time for that thing to warm up. There's a tube in there. It's a power supply inside that. Okay, so this reads voltage, this reads current. We're really only interested in the current as it shows up on the meter you can't see right now. But let's start up here, just in case things are wild. So voltage is 0, Okay, watching this meter, which is sitting on 0. Well, so what it's doing is it's charging. I don't know if you could see that, but as I turned up the voltage, this jumped up and then came down again. So it's just charging capacitors. Now we'll take a look at, from now on we'll watch this meter down here. It says 0. Okay, so we're going to go up, up, up. It's going to go back down to 0 probably, yeah, back down to 0. Yeah, this test is not going to do what I thought it was going to do because I forgot that the tubes have to be hot for this to really show the current draw. But what this does indicate though is the B+ circuit has no significant leaks in it in itself. There's no capacitor that's leaking badly. At least, at least in terms of 0.1 milliamps there. That's the minimum this can read. I've got about 150 volts on it now. Let's go a little higher. That's like 250. It's a charging current. Now everything's charged up. 0. You know what? I don't think I have this meter set right. This meter's not set right. That's why it wasn't showing the Earth's magnetic field. Okay, hold on. Ooh. Cut back, cut back, cut back. Yeah, that's why it didn't show the Earth's magnetic field. I should have thought harder. Didn't set it to current. There we are. Now we see the Earth's magnetic field problem. I'll 0 it. Now if I just rotate it at a little different angle, you start getting another reading because I'm picking up the Earth's field in a different way. Yeah. So these meters, you got a 0 in the position you're going to use them. Okay, so we have no current flowing here. 0 it. Let's try this again. Now it's 1.000 milliamps, or amps. So 1 milliamp is that. That's showing 1 milliamp. Probably just noise or something like that. Okay, let's crank it back up. Should still be some charge in it. Here we go. So this meter on the panel is jumping up to about 10 milliamps, but I can't look down at the other meter. This is showing a steady current flow up here, and it's showing a fairly steady one down here too. That's more what I was thinking. You got 125 milliamps nominally from the power supply. I'm looking for some reason that it's 200. This is not going to get me to 200. And it's possible there's something in the circuit that in fact is drawing this current normally. It's not a leaky capacitor. Probably is leaky capacitors. You're pushing with a couple hundred volts and you're getting 10, let's say 10 milliamps, a couple hundred volts. The power is E squared over R. It's too big a number from my head. Let's say it's actually 250. Let's say 250 volts squared. That's that big number I couldn't handle. And then divide by, oh yeah, what am I doing? I'm doing something stupid. I'm going to do it E squared over R. I don't know R. What I know is E and I. Come on, Jim. Come on, man. 250 volts times 15 milliamps. So that would be 0.015. That's 3 watts. Almost 4 watts. Watts, eh? Something's going to get warm. 4 watts would heat up, like a filament, like a light bulb filament, like a small light bulb. I wonder if this will build heat in here. So maybe I'll just let this run for quite a while, and then we'll see if something got warm. which I doubt we're going to find anything, but it's a good excuse for me to stop and drink some coffee. Yeah. Okay. Well, it's been maybe 5 minutes at the most, and this has gone up from 20 to 30. So whatever it is that it's heating up must be getting warm enough to detect. That's what I'm hoping. It's a bit of a long shot here. What are the chances? Okay, so I'm setting this. Whoops, I'm not. Hang on, I made a little mistake there. Something has to be 40 degrees to turn red. Well, close to 40 degrees. Now, can you see? You can't. Once again, I'm having trouble making this visible on the camera. But something's getting hot, quite hot down here. Wait a minute, it's over here. One of these resistors in here. I have a resistor right here. It's getting quite warm. How hot, Jim? How hot is it getting? 55. Well, there's where the heat's going. This is, I would guess, we'll have to look at the schematic now and try to understand what could be happening down here. Oh my gosh, there's a lot of stuff connected right in there. How are you ever going to figure that out? Wow. Oh, it's connected to a tube. It's connected to this tube here. So maybe we can trace these resistors off of this tube. Let's go see if anything else. That's pretty warm. That's got to be where most of the heat is going. We're up to 35 now. It's interesting that this is just climbing, because that would suggest something more like a like as a resistor heats up, its resistance goes up. So it's kind of self-healing in a way. It's really tricky. I'm looking through a hole here and for some reason seeing something warm on the other side. There's nothing over there. Maybe it could just be the bench top. So there's another one that's showing up warm here. Oh, this camera is really hard to aim at. No, it's not. It's all part of this. There's a very wide field of view on this camera. Like it's looking like really wide. So see if we can spot anything else here. Anything else anywhere else? Well, that's that same resistor again. I'll make this more sensitive and do this again. Make it too sensitive and it'll just show everything under the sun here. There's actually a number of resistors in here that are showing a fair bit of heat. I wonder how hot these were getting when I was operating the radio normally. So we're kind of steady at 39, almost 40 milliamps now. That resistor's warm. And these two. All these guys in here. Now this guy's meant to be warm. Look, it's a great big high wattage resistor. These aren't small guys either. And the way they're laid out, they're kind of spaced out and they're airborne in here. Probably it was known that these would get warm during the operation of the radio. Let's make this more sensitive now. Okay. That's about 5 degrees more sensitive. Could be seeing, as I explained last time I had this out, the emissivity variations in materials. On this device too, you can't see it, I'm sure. There's a red plus sign floating around. It's always marking the highest thing the camera is seeing. And it's reporting that temperature here, 24, 25, it's nothing. So I think the whole heating deal is happening over here. These capacitors are of interest too. Supposedly these are working right now. They're big, there's no sign of heat in them. The heat is all in these resistors here. So now the one resistor is cooking up at the highest temperature I am seeing right now is I can't read it. The numbers are too small. 56, about 60 degrees. The hottest thing in view is about 60 degrees. I put my finger on that, I would know it. Actually, your finger's a terrible thing to try to test the temperature with because it is slow. So by the time you really feel the heat, you burned yourself. It's too slow. This has gone up to 47 now. Is the voltage rising on my supply? It's right at 250 where I left it. The reading on the supply current is about, that's a lousy meter up there, a little under 10 milliamps. This thing's reading 48. Why is it beeping at me? Because I have to. Well, why would it beep at me? Don't beep at me. You're only good for so long. Is this real? Because the other meter is under 10. And this is 50. 50. I'm liable to feel a little bit of heat in some of these connections with 50 milliamps flowing. I don't feel anything. Is this for real? Or did this go off? Look at it. That's why I don't like using this meter. Let's zero it again. So for some reason the meter is drifting off. Why? Is it because the moon is moving above us? Now this says 8, 6, 8. It's matching the meter up above. I put this on because I thought this would be a better meter. Goodbye. What we're going to do is I'm going to insert a better ammeter right in this line now, and so we can get a much better idea of how much current is flowing. I'm also going to, before I do that, I'm going to think about how to fire up the tube heaters and get the tubes operating to get the full Monty on the current drain in this radio. How could I do that? You know, I could do that. There's one wire that's leaving here that's carrying all the B plus current. I could interrupt that wire and I'm sorry, and interrupt the wire and put an ammeter in there. We could operate this radio and we could see for sure what the real current is. I gotta think about that. That's interesting to do that. I could set that up. It's pretty easy with this radio in some secure fashion and have that operating almost continuously from here forward. I'm gonna think about that a bit. Okay, I think I'm ready to go. This turned out to be a pretty easy thing because I have the field coil plugged into the jack at the back here. I was able to unplug one, plug it right into my meter, and then connect my meter back to where the jack came from. So this is right on the field coil circuit. I still have this resistor sitting here. You know what? I don't think that's a good idea. I think I should remove it, and we'll look at the way the radio operates the way it is. I think that, well, no, I'll leave it there for now. I'll leave it there for now. We'll see what happens. Okay, we'll call it a dry run. So we'll turn this meter on. This is reading, the scale here is 200 milliamps. So I think these numbers would be in milliamps here. Okay, 125 is what we're looking for on the 200 milliamp scale. How do you get, there's no number here. Won't worry about it. I think the meter knows what it's doing, even if I don't. I also have this meter connected, and it's connected to the filter capacitor so we can read the B plus that's developing in the radio. I'm going to start real low here. I'm talking about low. Turn this way down. We're going to start with the dim bulbs and start low, just to make sure I got things in order here. What could I have done wrong? I don't think I could have done much wrong. Famous last words. Okay, dim bulbs on. Seem a little curious, there's nothing here. Guess the rectifier has to warm up first. And it could take a long time. We're running the radio with 70 volts right now. Let's crank it up a bit. I'm reading the voltage over here on a meter you can't see. 75 volts. Okay, so this is the point where I start thinking I haven't done something right. Well, we still don't really have any B plus over here. So, no surprise the radio's not operating. We're at 76 volts on it. Go a little higher. Well, we're getting a little bit of current now. 0.1 milliamps, I believe that's what that means. We still have virtually no voltage here. I'm going to drop the scale. This is now 150 volts full scale. And we're at 50 volts. 80 volts supply voltage. Still, this radio doesn't seem to work till you get up around 100. Okay, so I'm going to remove the dim bulbs. Okay, 85 volts. Nothing out of the speaker. Just a little higher voltage here. Okay, we're going to take it up now. I think, as I said, the set starts operating up around 90 or 100. That's 90, 95, it's 95 now. This is starting to go up more significantly. Ideally, this goes up to 315. It's nowhere near there. It's 100. And reading this is 0.3 milliamps. Still nothing. Nothing coming out. Okay, well, everything seems okay. Let's push it all the way now. We'll go up to 100 and something volts here. Radio's making sound. Still extremely low current reading here. Maybe I'm reading this meter wrong. So I'm reading that as 0.6 milliamps. Okay, on the 20 milliamp scale, it's over. So I'm not reading this right. So this got to be 60 milliamps. What a great! Of course, I pick a meter. I'm not sure how to read it. Look at this voltage has gone right over. I'm not watching. Just over 150 volts now. That's got to be 60 milliamps. 125 is the nominal flow, and this should be 300. So this should be up in this range normally. Supply voltage is 102 volts. Well, let's take it up to like 115 or something like that. Okay, that's 112. You can hear the distinct hum coming out of the speaker. It was never there before. Volume's up very high. It's full. Volume's full. B plus voltage is now 225, which is substantial. Current flow now is, I believe, I don't know how to read this meter. This is a problem, Jim. That's a big problem. We got to put a different meter here. Okay. Because I'm too stupid to be sure of what I'm doing here. What if we tried this one? Is it working? We got to be 200 milliamp DC volts. Amps. Oh, 200 microamps. Look at how sensitive this is. 2000, 20 milliamps. 200 milliamps. 200 milliamps. Ooh. ACA. What's that all about? Somebody's penciled on here. ACA. ACV. DC. So DC volts, AC volts. AC current? I don't think so. That's a DC symbol there. This got to be wrong. Another meter I can't be sure of. Come on, really? I think that's a DC symbol. No wonder whoever had this meter before me sold it at a yard sale and I bought it because they wrote the wrong thing here. It never worked right for them after that. Okay, we're gonna just take this guy out of the action here. I'm gonna put this guy in, and we want to put 10 amps, common. So amps. And the other one is here, common. Okay, I think I got the same setup. Now, the decimal point's in a weird place again. You can't get to 200. Oh my gosh, you'd think I'd know how to do this kind of stuff, but nah, maybe not. Let's let her rip. Now I got the voltage set high, but I got the dim bulbs in, so the voltage at the radio will be low again to start. There we go. So I think that's 2 milliamps. I think that's 3 now. Well, yeah. Okay, let's turn things up here. I just close my shop door in case some screaming starts happening here. I'm going to turn down the variable, turn off the dim bulbs. 6 milliamps, 7 milliamps, 10. Well, what happens when it gets up above 99? What's this meter do? Does it turn on another digit here? We might find out. Okay, so we still have no B+, 87 volts. The radio's not operating, can't hear a thing. Okay, we're going to take it up. Yeah, no, this is what you would expect, I think. 28, 29 milliamps. B+ is running around 150 volts. This is the same circumstance that fried this, cooked up that resistor. Let's take a look and see what's happening here. Generally speaking, what I'm doing here is having fun. That's generally what I'm really doing here. So, 45 degrees. Okay, so we see the same, you know what, they aren't. So what's heating up is this guy again, the one I put in, and these other ones, they're cool. You can hear interference from the meter. They're cool. Did I do something wrong last time? I don't get it. How come these resistors are cool this time? There's no heat in them. The only hot thing is this guy here, and he's cooking up at 75 degrees. 34 milliamps. Now, so that's certainly not excess current. 125 is what this radio says it draws. Let's push the voltage higher. We're only at 100 volts. Let's go higher. 110, 111, about 112 volts. Now we're getting a more reasonable current here. By now this resistor is just frying in here. It's going to start smelling. Yeah, it's getting up towards 100 degrees. So we can't do this for very long. So what happens if I remove the resistor now? We're going to do that. We're going to cut the resistor out of there. Actually, I'm going to stop. I'm going to desolder it. Yeah, I almost reached in and grabbed that resistor with my fingers. That might not have been a good move. I'm just going to leave it hanging out there. So now all the B plus is going through the field coil in the normal way. I'm going to repeat this test. All the field coil current passes through this meter. Ooh, that is hot. You know, this resistor was probably on its way to desoldering itself. The heat was probably going to travel up these wires and desolder it itself. It's getting that hot. If I let the thing go full, I'm pretty sure that it would have had some self-soldering radio here. Okay, we're ready again for another test. Crank down the supply voltage. Dim bulbs first. So the idea here is, the question is, does this radio draw an extra current beyond what it's supposed to draw when operating? And that's why things are getting hotter than I would expect. The current, according to the schematic, is 125 milliamps. We're going to find out what happens. Now I've got this field coil in here at a high resistance, so if this thing came up to 125, I'd be stunned. Stunned, I tell you. Okay, we're going to jump this up. Now the output tubes are drawing 50 milliamps. That's a pretty heavy current for a tube, I think, anyway. So we're at 30 milliamps. We really don't have the B plus going. We're at 95 volts on the supply. Crank it up. Radio's working now. So we're about roughly half the current that you would expect, and we're close to the full B plus here. So we'll put it up to 115 volts on the supply. That's close enough. So my expectation is we're pumping less current through that field coil than the radio would normally have. We're at 250 volts on the B plus, which sounds like it's good enough. 84 milliamps. Another interesting question then would be, what kind of current can you put through a field coil? What's a typical field coil current? What's a typical drain on a power supply like this? Assuming that's a typical speaker from another radio, maybe it can sustain this kind of current. Maybe 50 degrees C isn't so bad. This isn't showing me that there's some unusual drain of current in this radio, such as a bad capacitor like what was here. That bad capacitor probably only drew a few extra milliamps. It wouldn't have even appeared. A test like this I would never have gone aha. Just like I'm not going aha now. 113 volts on the radio. A little more than half the current expected. So what is the voltage drop happening across the field coil again? Let's just do this again, because now I can measure the amount of current. I know how much current's going through it. If I measure the voltage drop across it, how do I do that exactly? I'm on this meter. Well, one side would be low, the other side would be high. So that's 250. That's probably the high side. Okay, so there's the low side. So that is 30 volts. And the high side is 250. So 250, so it's about 220 volts dropping on the field coil. The whole thing is dropping on the field coil. So we got 250 volts and 87 milliamps. Let me shut the radio off. Probably do this with round numbers really quick, but let's do it this way. So what's the formula, Jim? I times E. It's easy. So we had 80 milliamps. That's 0.8. 0.8 times the voltage, 200. Was it 200? It was a lot. 200. No, 160 watts. No. No, it'd be making toast with that speaker if it was like that. Let's try this again. 80 milliamps. I know what I did. I did point. I should have done point. 0.08. What I should have done. That's what was wrong. 0.08. 80 milliamps times 200 volts. 16 watts. And the radio, the normal power supply is 125 at 300. So if you had 300 volts, more than 300 volts, and you've got 125 milliamps, which is 0.125, 37 watts dissipating in the B plus circuit. Probably mostly, well, I don't know. Where would most of that go? Maybe some resistors burning some of that up. Tube dissipation. Plate dissipation. I don't know. I've never done these numbers before. I never really thought about all of this. Not to this level before. 37 watts and 15 in the speaker. 15 watts in the speaker. Maybe I can find out on a wattage basis what these speakers are typically capable of. That's interesting. Look into that. Well, I thought I'd try Mr. AI first. So here's my sentence, and excuse my bad spelling of the word dissipate here. How many watts does a field coil on an antique speaker dissipate? You don't even have to spell things right. And here's what Microsoft Copilot says. Field coil in an antique speaker serves a dual purpose. Let's delve into its workings and the power it dissipates. Much better spelling. Magnet for the speaker. Field coil acts as electromagnetic within the speaker. Unlike modern speakers that use powerful permanent magnets, older speakers relied on field coils to create the necessary magnetic field. When current flows through the coiled wire of the field coil, it generates a magnetic field. This magnetic field interacts with the voice coil to produce sound. Essentially, the field coil serves as a magnet that enables the speaker coil. Okay, thanks for the basics. Filtering AC from DC. Filtering AC from DC. That's a weird way of putting it. The field coil also plays a role in filtering the power supply. Filtering the power supply for the speaker. That's not quite right. As current flows through the coil, the magnetic field it creates reacts with the current. It allows direct current to pass through while blocking alternating current. It doesn't quite block it, but in filter circuits, an inductor like a field coil is often referred to as a choke. Field coil choke, along with other components, forms a circuit called a pi filter. That's what's in this radio. Pi filter helps. It's called a pi filter because when you look at the components on a schematic, they're in the shape of the pi symbol. Smooth out the pulsating direct current from the rectifier, ensure stable. Okay, that's fine. Dissipation of power. The power dissipation of the field coil depends on its resistance and the current flowing through it. Thank you. To estimate the power dissipation, measure the field coil's resistance, then apply enough voltage to make it dissipate a couple of watts at most. Huh? To estimate the power dissipation, measure the field coil's resistance, and then apply enough voltage to make it dissipate a couple of watts at most. That doesn't make sense. Typically, a field coil speaker dissipates a small amount of power, usually a few watts. There we are. a few watts while performing its dual function. 15 watts, is that a few watts? I think that's more than a few. In summary, the field coil not only acts as a magnet, but also blah, 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 blah. Well, this didn't quite help. Few watts, that's what I'm after. Okay, I'm going to keep looking for more sources of information here. Let me just show you this this comment here. I'm just gonna. This is a page where somebody's field coil speakers, everything you need to know. But these aren't vintage field coil speakers. These are really big, whopping ones being built today for people who have just too much money. Look at this line here. This is typical of audiophile comments. Look at this. With field coil drivers being more dynamical, speedier, and capable of creating details with considerable more accuracy than the majority of standard magnetized speakers, they are set to make a major comeback in the near future. At the moment, though, only a few selected manufacturers are using this effective solution for superior musical presentation, and for those who value the highest quality sound, it is their speakers that should be a top purchasing choice. Well, they're trying to sell these speakers for an enormous amount of money. That's got to be what's going on. No, I think the magnetic field doesn't know where it came from, so, use a permanent magnet. Why would you do this? Because you have too much money. That's why. Choosing field coil speakers for outstanding quality. Well, yeah. This didn't help one bit, but I got a kick out of reading I just love hearing what audiophiles have to say about the quality of sound, because it's always kind of goofy what they say. Okay, that's all. Okay, finally, some synapses appear to have communicated properly in my brain here. This says the output at this point, the voltage is 315, and when you get to the other side of the field coil, the voltage is 245. So we know the voltage drop that this radio expects across the field coil. 245 from 315. So that's 235 from 305, 230, so it's 70 volts. And a 70 volt drop. And I'm getting a 200 volt drop. So 70 volts is quite a bit. Kind of surprising to me in a way. Let's just double check what I'm doing here. 315 on this, and through the field coil. And yeah, 245 right there. So that also gives me the wattage that they expected to dissipate from it, and just using the voltage and the current. So if we had a calculator, I could do this. We have a calculator. So what were those numbers again? That was 70 volts times 125 milliamps, 0.125, 8 watts. So this suggests 10 watts dissipated in the field coil, roughly. Nominally, but in actuality, I'm doing 15 watts in this speaker and coming out with very low B+, although the radio operates. Now, why when I stick a high wattage resistor in parallel with it, why does everything go wonky? Why does this thing cook? I need to measure the current split. Why would I bother doing that? I know what the resistance of the field coil is. The current split here is roughly 50-50. But at the same time, because this is boosting the B+, I assume this is boosting the B+, the radio then draws more current. It's a dynamic situation, or too many variables happening at once, and so the end result could be more current leaving the power supply, same current going through the field coil, and a bunch of current going through this resistor, cooking it, because the B+ went up. And I think about how to experiment with this. Was I standing in front of there? It doesn't really matter, does it? Okay, I got to think about how to experiment further here. Okay, ready for another test here. So now, this meter is reading the current through the field coil. I've reconnected the resistor here. This is going to read just the field coil. There's more current passing through the resistor. And I'm going to burn this clip here if I don't move it. It's up against the resistor. Let's do it like that. This guy is reading the voltage across the field coil or the resistor, whichever one you want to. Think of it as reading both. Current through the field coil, voltage across the field coil. And this guy's still reading the total B plus on the radio. The objective here is to see clearly what the current is in the field coil when the resistor is connected. That's the objective. Okay, I think it's going to work. Let's just turn this way down. There we go. Dim bulbs first. Nothing weird happening. Give it a moment. Turn it up a bit. And like 70 volts. Of course, the last thing I can be doing is I can be reading the temperature of the resistor, which is nothing yet. A little bit surprising, there's nothing there, okay? Let's go up in voltage here. So 90 volts now. 10 milliamps going through the field coil. 20 volts dropping across it. 10 times 20. Not 20 milliamps. 0.01 times 20. Can't do it. It sounds like a couple watts to me. We don't know the current through the resistor. Okay, so B plus is nowhere near where it needs to go. And we need that pointing straight up to make this test valid. How hot is the resistor getting? Not getting very hot at all. I wonder if I soldered it properly. Not very hot. Radio not operating yet. Let's go higher. Okay, we're up around 100 volt supply. This is starting to rise now. You can hear the radio starting to work. There's now 25 milliamps going through the field coil. The rest of it, whatever it is going through that resistor. The resistor is starting to get a little warm. 30. We know the current in the resistor because we know the resistance, we know the voltage across it. It's 50 volts. So we can calculate that. But we want to get this up to its normal level and then take the readings and make the calculations. Okay, let's do that because everything's heating up while I'm standing here. So we want to go up to like about 115 volts or so on the supply. Okay, we're 116 volts, 220 B plus. There's my pencil. Yeah, I did not get a piece of paper and a pencil ready. Okay, so we're looking at 60 milliamps and we're dropping 100 volts. And the radio's operating. Now how hot is that resistor? And the resistor is frying up at 100 degrees, over 100. And it's probably just going to keep going higher. What did I write down? 60 and 100. 64 and 112. Let's write those numbers down. 65, it's still going up. Why is it going up, up, up? Work well. I guess the tubes are still heating up. Okay, write those numbers down. 66 milliamps, 116 volts. Temperature of the resistor is really hot. 100 over 130. That's too hot. She's over. The test is over. That's the result. What do we make of this now? Well, let's calculate the current through the resistor, say under this circumstance. So it's 116 volts dropping across the resistor. And the resistor is 2,000 ohms. Where's my calculator? I equals E over R. So we go 116 volts, and we divide it by 2,000 omegas. We get 5.8 watts. Is that what that is? Wait a minute, that doesn't look right. That's a little tiny number. What did I do? Repeat. 100, so it's I times E. 116. Good calculator. 116 times 0.06. Then is that what I did wrong? No, I don't think so. $7 watts. How did I get these two different numbers here? It's in the 5 watt range. It's in the range of the rating of this resistor. It's at the top range of the rating of that resistor. And the other, what am I doing here? I'm doing something wrong, aren't I? I did something wrong here. This is the wrong calculation. This is more the calculation for the field coil, but not quite. That is the calculation for the field coil. 7 watts. For the resistor, it's I squared R, Jim. So I squared was 66.066 times, is there a square thing here? Times 0.0666. What a lousy calculator. So we multiply that times the voltage drop, 116. Half a watt. Something terribly wrong here with what I'm doing. Something is terribly wrong. Something is really wrong. How can you get half a watt and this thing's cooking? Because you've done something wrong, Jim. Try it again. Let's try it again here. I squared R. I squared R. What did I do? I think I did it right. I squared 0.066. 66 milliamps. 66 milliamps times 0.066, a very small number, times 2,000. Is that what I did wrong? That's more like it. 8.7 watts. That's correct. I got the voltage and the resistance. I'm going to mix it all up here. So 8.7 watts. See, basically, the way this works is you do calculations until you get a number that's satisfactory, and then you go, that must be it. So 8 watts would explain why this thing is cooking. Almost 9 watts. On the other side, 60. Let's do that one now. 66 milliamps. So this is the voltage drop and the current through. So we multiply those two to get the wattage. The current through was 66. You know, I calculated the wattage here wrong again. Duh. I know the voltage and I know the resistance. So it should be E squared over R. Let's try that. E squared over R. You know, once again, you just continue making calculations until you get something that you're happy with. Times 116. And then we divide that by 2 by the... I'm so stupid. I'm brainless here. Once again, we know the current and we know the voltage. What a dork. I tell you, I'm really, this is embarrassing. Big time here. Times 0.066. Very similar, 7 watts. For a total of 15 watts. Yeah, that's really what it should add up to, isn't it? Each one's doing 7. That's roughly half. That's roughly split in half. The problem is it's 15 watts. And 15 watts still sounds like too much for a field coil. And I haven't found any information that tells me. Although, you know what? I can find it in books and just calculate the amount of current and the amount of voltage, if I can find it. I found it here with this one. That's where I got the, is that where I got the 15 watts from? It thinks the original speaker was doing 15 watts. You know, it wouldn't matter what the field coil resistance is or anything. 15 watts is 15 watts. Let's look again. Just the level of stupidity today is really stunning me here. If we've got, what was I doing? Oh my God! There's like the room effect here. As soon as I look at the screen, I can't remember why I even did this. Oh my God! Think, man. We wanted to determine the amount of current and voltage, so we know the voltage dropping. I already did this. I did this once. 315, 245, 70 volts. I did 70 volts at 125 milliamps. Will give you the so let me calculate. 70 volts at 125 millivolts. That's where the 15 came from. I better repeat it, just considering how things have gone with this calculator today. What were those numbers? Room effect, room effect. Every time I look away, my brain goes to clean slate mode. So we were talking about 70 volts, and the current was 125.125. 8 watts. What am I doing? My God, the world is coming to an end here. So let's try. Let's try that again. Try that again. 70 volts dropping across a 600 ohm field coil. I could do it that way. So that would be E squared over R. So that would be 70 times 70 divided by 600 ohms, the expected resistance. 8 watts again. So it looks like the schematic is suggesting 8 watts dissipation in the field coil. And here I'm in that range, aren't I? 8 watts in the field coil. The problem is this resistor just can't take it. It can't take it. I need a bigger wattage resistor there, like a 10 watt resistor. We'll see if that can solve that. Can I solve it that way? Can I find a 10 watt resistor at that? I don't know. Good luck to me. So I'm back from the grocery store. So I think I'm going to call it quits here at this point today. Just to kind of recap the situation. Yeah, I don't know how to recap this. I think probably my next step will be to try to find a higher wattage resistor that I can put in here that's going to somehow help the situation out. It looks like without the resistor, the speaker's on its way to overheating, getting hotter than I want. With the resistor, some of that heat's going to be dissipated in the back of the radio here, which isn't the greatest thing either, but I will I will come in here tomorrow and carry on. That's the plan. Thanks a lot for watching. I know this is kind of a screwy situation, but so be it. See ya.